Now that we know that there are two types of studies, observational studies and designed experiments, we're going to learn a little bit about designed experiments. We're going to describe the characteristics of an experiment, explain the steps in designing an experiment, explain the completely randomized design, explain the matched pairs design. An experiment is a control study conducted to determine the effect of varying one or more explanatory variables or factors has on a response variable. Any combination of the values of the factors is called a treatment. Usually we use designed experiment to test a drug. The experimental unit or the subject is a person, it's an object, or some other well-defined item upon which a treatment is applied. A control group serves as a baseline treatment that can be used to compare to other treatments. A placebo is its innocuous medication, such as sugar tablet that looks, tastes, and smells like the experimental medication. Blinding refers to non-disclosure of the treatment an experimental unit is receiving. A single-blind experiment is one in which the experimental unit or subject does not know which treatment he or she is receiving. A double-blind experiment is one in which neither the experimental unit nor the researcher in the contact with the experimental unit knows which treatment the experimental unit is receiving. Here is an example for the characteristics of an experiment. The English department of a community college is considering adopting an online version of the freshman English course. To compare the new online course to the traditional course, an English department faculty member randomly splits a section of her course. Half of the students receive the traditional course and the other half is given an online version. At the end of the semester, both groups will be given a test to determine which performed better. So in this case, the experimental units in this experiment are going to be the students in the class. The population for which the study applies is the students in the class. The treatment here is traditional versus online instructions. The response variable is the exam score. Why can't this experiment be conducted with blinding? Because both the students and the instructor know which treatment they are receiving. You can't hide that. To design an experiment means to describe the overall plan in conducting the experiment. The steps in conducting an experiment include, first, identify the problem to be solved. That should be done very explicitly. It should provide the experimenter directions, should identify the response variable and the population to be studied. This step is often referred to as the claim. The second step is to determine the factors that affect the response variable. Once the factors are identified, it must be determined which factors are to be fixed and at some predetermined level, the control, which factors will be manipulated and which factors will be uncontrolled. The third step is to determine the number of experimental units. As a general rule, choose as many experimental units as time and money allow. Techniques exist for determining sample size provided certain information is available. The fourth step is to determine the level of the predictor variable. Control. There are two ways to control the factors. First, to set the level of a factor at one value throughout the experiment if you're not interested in its effect on the response variable. Or we set the level of a factor at a various level if you are interested in its effect on the response variable. The combinations of the levels of all varied factors constitute the treatment in the experiment. Conduct the experiment. Replications occurs when each treatment is applied to more than one experimental unit. This helps to assure that the effect of a treatment is not due to some characteristics of a single experimental unit. It is recommended that each treatment group have the same number of experimental units. Collect and process the data by measuring the values of the response variable for each replication. Any difference in the value of the response variable is a result of differences in the level of the treatment. Then we're going to test the claim. This is the subject of inferential statistics. Inferential statistics is the process in which generalization about the population are made on the basis of results obtained from the sample. Provide a statement regarding the level of confidence in the generalization. Methods of inferential statistics are presented later in the text. So we're going to do that later on this semester. We're going now to explain the completely randomized design. A completely randomized design is one in which each experimental unit is randomly assigned to a treatment. An example, the octane of fuel is a measure of its resistance to detonation, with a higher number indicated higher resistance. An engineer wants to know whether the level of octane in gasoline affects the gas mileage of an automobile. Assist the engineer in designing an experiment. The response variable in this experiment is miles per gallon. The factors that affect miles per gallon are engine size, outside temperature, driving style, driving conditions, characteristics of car. We will use 12 cars, all of the same model and year. We list the variables and their level. So octane level, manipulated at 3 levels. Treatment A, 87 octane. Treatment B, 89 octane, and treatment C, 92 octane. Engine size is going to be fixed because we're working with the same model and year of the car. Temperature is uncontrolled, but will be the same for all 12 cars. Driving style conditions, all 12 cars will be driven under the same conditions on a closed track. That is fixed. Other characteristics of car, all 12 cars will be the same model, year. However, there is probably variation from car to car. To account for this, we randomly assign the cars to the octane level. Then we randomly assign 4 cars to the 87 octane, 4 cars to the 89 octane, and 4 cars to the 92 octane. Then give each car 3 gallons of gasoline, drive the cars until they run out of gas, compute the miles per gallon. Finally, we're going to determine whether any differences exist in miles per gallon. So here is an illustration of what we just did. We took 12 cars, we controlled some variables, and then we took each 4 cars and assigned them to a different octane. And then we drove those cars under the same conditions and then compared the miles per gallon. The next design experiment is matched pair design. A matched pair design is an experimental design in which the experimental units are paired up. The pairs are matched up so that they are somehow related. This is the same person before and after a treatment, twins, husband and wife, same geographical location, and so on. There are only 2 levels of treatment in a matched pairs design. Here's an example. Xylitol has proven effective in preventing dental cavities when included in food or gum. A total of 75 Peruvian children were given milk with and without xylitol and were asked to evaluate the taste of each. The researchers measured the children's ratings of the 2 types of milk. So, what is the response variable in this experiment? It is the rating. Think about some of the factors in the study. Which are controlled and which factor is manipulated? The controlled factors are the age of the children, the gender of the children, milk with or without. Xylitol is the factor that was manipulated. So either the kids were provided or given milk with xylitol or milk without a xylitol. So that is the factor that was manipulated in the experiment. What are the treatments? How many treatments are there? There are 2 treatments in this experiment, which namely are milk with xylitol and milk without a xylitol. What type of experimental design is this? This is a matched pairs design. We want to identify the experimental units. That's the 75 Peruvian children that were in the study. Why would it be a good idea to randomly assign whether the child drinks the milk with xylitol first or second? To remove any effect due to order in which milk is drunk. Do you think it would be a good idea to double blind this experiment? yes, it's going to be a good idea to double blind this experiment. So neither the kids nor the researcher know which milk has xylitol and which milk doesn't have a xylitol.